Hi, in this video we're going to be looking at another problem involving connected particles where the objects will be moving all in the same direction. And we're going to look at a classic problem involving a trailer that will be attached to a car. Now, when we're looking at problems involving connected particles where the objects are moving in the same direction, we could set up an equation of motion for each of the two particles separately, or we can also treat the whole system as a single particle. So let's have a look at the problem that we have got in front of us. So we've got a car which has a mass of 800 kilograms and it's going to pull a trailer of mass 200 kilograms along a straight horizontal road using a light tow bar which is parallel to the road. So let's just go ahead and just draw that little diagram, and then we'll start adding on all of the other forces that are listed within the question. So here's our road, and we're going to have a car. Now I'm just going to draw some simple boxes just to illustrate these objects. So this is going to be the car, and behind the car we're going to have a trailer, and what do we know about the car? The car has a mass of 800 kilograms, and we've got a trailer which has a mass of 200 kilograms, and they are connected by a light tow bar which is parallel to the road. So we can indicate that as such. We've got some horizontal resistance forces to motion of the car and the trailer, and they have magnitudes 400 newtons and 200 newtons respectively. What does that mean? Well, since the car is mentioned first and the resistance force of 400 newtons is mentioned first, means the car will have a constant resistance force of 400 newtons. So we can indicate that on the diagram. So let's do that. So the car has a constant resistance force of 400 newtons. I've put this resistance force acting towards the left. That's because the car will be in motion pulling the trailer towards the right. So it might be sensible just putting in the direction that the car is moving in. So we know all the resistance forces have to be acting in the opposite direction to motion. And just quickly going back to the trailer, we're told that the trailer will have a resistance force of 200 newtons. So we can also include that on the diagram as well. What else do we know? It says the engine of the car produces a constant horizontal driving force of magnitude 1200 newtons. So the driving force will be acting towards the right. So we can indicate that as such. And we do have another force that we haven't yet included. See, the trailer is connected to the car by this light tow bar which is parallel to the road. So there's going to be tension in the tow bar. Clearly, if the car is producing a driving force, we obviously want the trailer to be attached to the car. So therefore we don't want the trailer to separate from the car, and therefore we are going to have tension forces in the tow bar acting towards each other. So here's our diagram. So we've got all of our horizontal forces, since motion is taking place in the horizontal sense. Now from this diagram we can actually set up a number of different equations. We can set up an equation of motion for the trailer, we can set up an equation of motion for the car, and we can set up an equation of motion for the entire system, the whole system. If we treat it as one whole system, we can also set up an equation of motion. Now if you're ever confused how to actually start a question like this, it might be better just to set up the 3 equations of motion for each of the 2 particles and the whole system. Okay, now I'm just going to quickly do that just to show you exactly what it looks like. Okay, so the first thing is we're going to look at all the forces acting on the trailer. So how many forces are there acting on the trailer? Well, on the trailer we've got this tension force acting towards the right, and we've got this resistance force of 200 newtons acting in the opposite direction to motion. So we can set up, using F equals ma, an equation of motion for the trailer. So let's just put a little indicator here. So we're going to set up an equation of motion here for the trailer, and remember we're using F equals ma because the objects are in motion, and we need to resolve towards the right. So resolving horizontally, well, we've got tension in the trailer acting in the horizontal sense, and we've got its resistance force of 200 newtons acting towards the left. So therefore its resultant force would be given by T minus 200. And that's going to be equal to the mass of the trailer, which is 200 kilograms, multiplied by the acceleration, which we don't yet know in the question. So we're just going to write it as 200 times A. Now you can see there's an issue with this equation here straight away, because we can't use it since we don't know what A is, the acceleration, and nor do we know what T tension is. But that's an equation of motion for the trailer. We can do the same thing for the car. So what forces are there acting on the car? Well, we've got this driving force acting on the car, acting towards the right. We've got this resistance force of 400 newtons acting towards the left. And we've also got tension in the tow bar acting towards the left. So that means we've got 1, 2, 3 forces acting on the car. So again, we can set up an equation of motion for the car, and since it's accelerating towards the right, we can resolve and set up the resultant force to be written as 1200 newtons, which is also acting towards the right. And we've got these resistance force of 400 newtons and tension acting towards the left as well. So they would be given by minus 400 minus T, and that would be equal to the mass of the car, which is 800 kilograms, and multiplied by the acceleration A, which again we don't know. So again, in this equation we've got 2 unknowns. We've got acceleration and tension, which is unknown. We can actually tidy up this second equation, because 1200 take away 400 gives you 800, so hence this would become 800 minus T is equal to 800 multiplied by the acceleration A. So since we've got equation for the trailer, which we're just going to label as number 1, and we've got an equation for the car, which we're going to label as number 2, you could go ahead and solve these 2 equations simultaneously, and hence you can determine the magnitude of A, and also you can determine the magnitude of T. Now that's just setting up the 2 equations of motion, one for the trailer and one for the car. Now, since they're both moving in the same direction, we can actually treat the model as one whole system. So let's set up an equation of motion for that scenario. Okay, so if we treat it as a whole system, what forces do we have all together? Well, we've got 1200 newtons acting towards the right, we've got 400 newtons acting towards the left, we've got 200 newtons acting towards the left, we've got tension acting towards the left and tension acting towards the right. And we would need to have a look at the entire mass of both the car and the trailer together. So what's this equation of motion going to look like? Well, it's accelerating towards the right, So we've got 1,200 newtons as our driving force. Let's take off our two resistance forces, 400 newtons and 200 newtons. Remember, they're acting towards the left. We've got negative T and positive T. So negative tension and positive tension. So altogether there were 5 forces acting on the entire system. And if we're looking at F equals ma as a whole system, we're going to look at the total mass of the system. 800 kilograms combined with 200 kilograms, well, that makes 1,000 kilograms. And that would be multiplied by the acceleration a. And it might be an idea to tidy this equation up a little bit. So 1,200, subtract 400, subtract 200 will give you 600 newtons. So that will be 600. And negative T plus T, well, they cancel. They disappear. And this would be equal to 1,000 multiplied by acceleration. So we've got basically 3 equations of motion. Now, remember what I said earlier, if you're struggling to decide how to actually start a question, once you've got your diagram with all the forces clearly labelled, you can start writing the 3 equations, one for each particle. Since we've got 2 particles, we've got 2 equations, and one for the entire system. And then you can decide what's the best route to take to go ahead and solve. Now observe, equation number 3 only has one unknown in the equation, whereas equation number 1 and 2, we've got acceleration and tension. So if you were to ask yourself which one would be the best equation to work with to calculate any of the unknowns, equation number 3 would be the better one to use, since there's only one unknown. Well, let's go ahead and calculate that unknown, and that would help us answer part A of this question. From number 3, we can say that acceleration is equal to 600 divided by 1,000, and that's going to give you 0.6 meters per second squared. So we've actually answered part A of this question. Right, let's have a look at part B of the question. So part B of the question says we need to find the magnitude of the tension in the tow bar. So since we now know what acceleration is equal to, we can now go back and have a look at equation number 1 to calculate tension, or we can have a look at equation number 2 to calculate tension. And again, it doesn't matter which of those 2 equations you use, you can calculate tension from either one of those. So I'm just going to use number 1. So for part B of the question, we're going to say, well, from number 1, we've got tension minus 200 is equal to 200 multiplied by 0.6, and we can now rearrange to work out tension, and tension would work out to be 320 newtons. So that's the answer to part B of the question. So if there's a driving force being applied to the car, we will have tension acting towards each other. Okay, I'm just going to put a little note on this diagram over here. So we had a driving force scenario. So when we've got a driving force scenario, we will always have tension in the tow bar acting towards each other. We don't want the trailer to separate from the car, so therefore we'll have the forces acting towards each other. Now, the second part of this question says the car is moving along the road when the driver sees a hazard. He reduces the force produced by the engine to 0 and then applies the brakes. The brakes produce a force on the car of magnitude F newtons, and the car and the trailer will begin to decelerate. So the car and the trailer will still continue to move towards the right, but they will be slowing down, and they will be slowing down because a braking force is now being applied. So how's that going to change our diagram? Well, let's go ahead and redraw the diagram again, and let's start including some new forces on this diagram. So here's our new diagram, and the resistance forces are unchanged, and we now need to add a few extra forces on this particular diagram. Now observe, we're still moving towards the right, but we will be decelerating. So what can we say about the value of our acceleration? Would it be positive or negative? Well, if we're decelerating, the acceleration would be a negative value. So that's just something to think about as we're working through this particular problem. Now we're going to apply a braking force. Now a driving force meant that the force was being applied towards the right in the direction of motion. However, a braking force would be applied in the opposite direction because we want to try to bring the car to rest. So we're going to apply a braking force acting towards the left. And the braking force will have magnitude F newtons. So we just indicate that on the diagram. If we now apply a braking force, then what's going to happen to the forces in the tow bar? Well, the forces in the tow bar will now be acting in the opposite direction to what they were before. So now the thrust forces, as we now call them, will be acting away from each other. Now when we had a driving force, let's just go back to the other diagram. When we had a driving force, the forces were acting towards each other. But when we now apply a braking force, the forces in the tow bar would be acting away from each other. And why is that? Well, we don't want the trailer to come crashing into the back of the car when the force is now being applied. So therefore, to prevent the trailer from coming towards the back of the car, we will now have the forces acting away from each other. So we need to determine what the magnitude of F, the braking force, is going to be, given that the thrust in the tow bar will now be 100 newtons. So we can indicate that on the diagram. So your tension forces here will be 100 newtons and 100 newtons. So how can we calculate the magnitude of our braking force? Well, again, if you're unsure, you can set up your equations of motion for each particle and the whole system, and we can take it from there. So for the trailer, we're going to apply F equals ma. So what forces do we have acting on the trailer? Well, we have a thrust force of 100 newtons acting towards the left. We have the resistance force also acting towards the left, and they're the only two forces acting on the trailer. So therefore, the resultant force acting on the trailer will be given by negative 200 and negative 100. So minus 200 newtons for the resistance force and minus 100 newtons for the thrust force. And that's going to be equal to the mass of the trailer, which is 200, multiplied by the acceleration. Now remember here, the acceleration of the system, it's now decelerating. So we can't use the same acceleration value as we obtained earlier. we'll have to recalculate this new value for the acceleration a. And just by looking at this one equation, this is a really nice equation, there's only one unknown. So we can actually go ahead and now solve for a. So now let's set up an equation of motion for the car. So how many forces are there acting on the car? Well, we've got our braking force, F, acting towards the left. We've got our resistance force on the car of 400 newtons acting towards the left. And we've got our thrust in the tow bar of 100 newtons acting towards the right. So our equation of motion for the car would be written as negative F minus 400 plus the thrust in the tow bar, which is 100 newtons, and that would be equal to the mass of the car, 800, times the acceleration a. Now we can tidy this equation up. So we're going to have minus F minus 300, and that would be equal to 800 multiplied by the acceleration, which is minus 1.5. So the magnitude of the braking force is 900 newtons. Now remember, that's not the only way to calculate the magnitude of F in this case. We could have looked at the whole system as one particle. So this was an example of a trailer attached to a car where we had to look at two different types of scenarios. One where a driving force was being applied, and just remember, if a driving force is being applied, the force in the tow bar will always be acting towards each other. And the second scenario was where a braking force is being applied, and if a braking force is being applied, you would have thrust in the tow bar and they will be acting away from each other. So I hope you enjoyed this tutorial and hope you've got a better understanding in tackling these types of questions. If you haven't yet subscribed to the channel, please subscribe so that you can receive regular updates on new video tutorials. Thank you.